Hello students, a very good afternoon to all of you. I hope your day is going good and you are still full of energy to attend today's lecture. So in the previous class we have covered electric field due to different configurations, right? Today also we will continue the same, and then we will also study about motion of a charged particle in the presence of electric field, how it changes and how the presence of electric field in a region impacts the motion of charged particle. Okay, so whatever we are studying in our classes here, after the class you can check out the PDF of today's class or the previous classes even in the eCareerPoint app, which you have to download from Google Play Store. Okay, so if you require the PDF of the class or the previous classes, you can download it from the free section tab which is given in the app. So please download it, explore it and use as much as you can, because these are free resources available to you, so that you can judge properly like what is useful and what is not useful, and you can get benefited of it. Okay, so let's start with our today's class. So in the last class, previous class, I covered electric field strength due to a uniformly charged ring. Okay, so today let's find out what will be electric field strength due to a uniformly charged disk. Okay, so till now we have no idea, I have no idea of any direct formula. Until I derive it, I have no idea how I am supposed to find electric field strength due to a uniformly charged disk. What do we mean by saying uniformly charged disk here? See, all over the surface of the disk, let's say the radius of this disk is capital R. Okay, all over the surface, what is the charge? All over the surface positive charge is present. Let's say like this, positive charge everywhere. I have one already derived formula for uniformly charged ring. Okay, if I take an elemental ring, in between this somewhere like this, let's say I am cutting a small elemental ring from the surface area of the disk. Okay, let's say this radius of the ring is given by y, and the thickness of this elemental ring is given by dy. In that case, I have to find electric field at point P due to the whole disk. I am supposed to find electric field due to the whole disk at point P. So what I have considered? I have considered an elemental ring on the surface area of the disk. So first of all, what I will do, I will find out electric field due to this elemental ring at point P, and then I will integrate it for the whole disk. Okay, so one formula we already know. That for a uniformly charged ring, like this, if this is the uniformly charged ring, due to this, if I have to find electric field at point P, which is at a distance x from the center of the ring, then the formula which we have derived is electric field EP at this point. EP is given by K, if the charge here is capital Q, then I write KQ x divided by x square plus r square raised to power 3 by 2. So due to a ring, this is the formula which we already know. So using the same, since I have taken an elemental ring here, I will use the formula for electric field due to a ring at an axial point directly here. Okay, so what I will do in this case, what we can do in this case is, due to this ring which is of radius y, I am trying to find out electric field here. Let's say the electric field here due to that ring is dE. So I can write dE is equals to how much? Let's say the charge here is dq, the charge on total is, let's say charge density sigma is given, sigma coulomb per meter square, charge per unit area. Charge density, that is charge per unit area, is given to us, that is sigma coulomb per meter square. Now what we are supposed to do, we are supposed to find electric field due to this small elemental ring, and then we will integrate it to find out electric field due to the whole disk. Okay. Now dE I am writing, what will be the magnitude of dE? Taking inference from the same formula which we have already derived, I am writing K as it is. Instead of Q, I am writing charge of this elemental ring, that is dQ, into what is the distance of this P point from the center. Let's say distance is x. So I am writing K dQx divided by x square plus radius of the ring y square raised to power 3 by 2. Okay. This is the formula for electric field due to this elemental ring. What can I write instead of charge dQ? So if I have to write dQ, I can actually mention dQ like this: sigma, that is charge per unit area for the surface of this disk, into area of the elemental ring. Area of elemental ring will be given by, see what is the length of this ring, what is the length of this small ring. The length of this small ring will be equals to the circumference of the ring. So what I am writing, for writing the area, I am writing circumference, that is length 2 pi y into thickness of the ring. That's what we write area, right? Length into breadth. So that's what I am doing, length of the ring into width of the ring, that is 2 pi y dy. So this can be written as our charge possessed by this elemental ring when surface charge density is sigma. So let's proceed. K sigma 2 pi y dy x upon x square plus y square raised to power 3 by 2. So this is electric field due to this elemental ring. If I have to find electric field due to the whole disk, I can write E net is equals to integration of dE, integration of K sigma 2 pi y dy into x divided by x square plus y square raised to power 3 by 2. So this integration we have to do from where to where? Because our variable is y, x is a fixed value, capital R is a fixed value, all are fixed value except variable y. Because radius of y will be changing, we will take rings of different radius so that we are able to make the whole disk. Okay. So I will tell you, take it from 0 to capital R. Okay. The limit is being applied on the variable y, because y is the variable here for different radius of the ring elements which we are using. Now I will continue with this integral from here. So what is the integral? I will rewrite. E net will be equals to K 2 pi sigma. I am taking this expression out, okay, and also I am taking x out. So what I am writing, K 2 pi sigma x, K, that is 1 upon 4 pi epsilon naught 2 pi sigma x. Okay, this I have taken outside. K 2 pi sigma and x I have taken outside. Y dy will be remaining inside. So I can write y dy divided by x square plus y square raised to power 3 by 2 integration from 0 to capital R. Now we are having this integral. We can cancel 2 pi with 4 pi and write 2 here. So this expression will become sigma x divided by 2 epsilon naught and integration of y dy upon x square plus y square raised to power 3 by 2 0 to capital R. Okay. So let's integrate this. Let's find out this expression. So this sigma x by 2 epsilon naught is constant and this remaining integral I have to find out. So put y is equals to x tan theta. If I put y is equals to x tan theta, I can write dy is equals to x sec square theta d theta. I can write dy as x sec square theta d theta, and also I can say x square plus y square will be equals to x square sec square theta. Okay. So x square plus y square raised to power 3 by 2 will become equals to x cube sec cube theta. So now since I know all the values, let's put them there. Integral of y dy upon x square plus y square raised to power 3 by 2 will actually change to, instead of y, what I will put, x tan theta. So I am writing x tan theta instead of y, and then instead of dy, what we have calculated, x square sec square theta d theta is the value. So x sec square theta d theta is the value which we are writing, divided by x square plus y square raised to power 3 by 2. So where is x square plus y square raised to power 3 by 2? This is x cube sec cube theta. So I am mentioning it here. X cube sec cube theta. And the integral is still there. I have just transformed y dy upon x square plus y square raised to power 3 by 2 by putting y is equals to x tan theta and finding out the remaining values like that. Okay. Aman Verma present. Hello Aman, how are you? Now x and x we can cancel by x cube and only one x will be remaining. Sec square theta I can cancel and only one sec theta will be remaining. Okay. So from here what we can say, from this expression we are getting 1 upon x as it is, tan theta upon sec theta will give us how much? Sin theta by cos theta upon sec theta, 1 by cos theta. So you can say sin theta d theta is the remaining expression. Integration of sin theta will be 1 upon x into integration of sin theta is minus cos theta. Okay. So if we are having tan theta is equals to y by x, if we are having tan theta is equals to y by x, no, I will not speak in Hindi here because this channel is meant for English only, Aman. Okay. So we will abide by English here. For Hindi there is a different channel, we will continue there. Okay. So tan theta is equals to y by x. If tan theta is equals to y by x, what we can do here? We can make a triangle. If this is theta, this is y, this is x. So you can say this is y square plus x square under root. Is that clear? So now what we can say, 1 upon x, and instead of value minus cos theta I can mention minus of cos theta will be base by hypotenuse. So what is base? X is base, hypotenuse is under root of x square plus y square. Is that clear? So now once we have got the value of the integral, now actually I can write my value, answer. What is that? E net is equals to, see what is the expression here, sigma x by 2 epsilon naught, sigma x by 2 epsilon naught, and the value of integral. What is the value of integral? We have already calculated, 1 by x into minus x upon under root x square plus y square, and the limits are from 0 to r, from 0 to capital R. So from here we can cancel x and x. If we cancel this, what will be remaining? E net is equals to, what will be coming? E net is equals to sigma by 2 epsilon naught in bracket 1 minus x divided by under root x square plus r square. Is that clear? So that will be our answer for net electric field due to a disk at an axial point P. Let's highlight the answer. Let's highlight this so that it is visible clearly to you. So this will be electric field due to a disk at an axial point. Is that clear? No problem? Let's proceed. So remember this formula because it will be very handy when you will be doing questions or problems based on this. Uniformly charged disk as a limiting case of large sheet. So basically what I am trying to say is, see, if I have calculated something, some value for a disk, what is the value we have calculated? This I have calculated for a disk. Okay, using this formula I can find out the value of electric field due to a very large sheet as well. Okay, so due to a very large sheet where charge is uniformly distributed and charge density is given as sigma, we can use this formula again, and we will do a very small significant but valuable change. Okay, valuable change in this formula, and we will get the value of electric field due to a very large sheet which is having uniform charge density as sigma. Okay, remember this formula, we will use it. So I am trying to find out electric field due to a uniformly charged disk or uniformly charged large sheet. Okay, with the help of the formula which I have got for disk. Okay, so for this disk we have, suppose we have placed a point P in front of the disk. Okay, this point P is very near or is having very less distance from the disk, or you can say the disk is so big in size that the distance of point P on the axis is insignificant. So I am writing here, see, focus, this disk is enlarging, this is becoming sheet, so the point becomes insignificant. If the point is very close and the disk size is very big, it behaves as an infinite sheet. Do you agree or not? So instead of R, what was the formula we have got? See, the formula which we have got here is sigma by 2 epsilon naught 1 minus x upon under root x square plus r square. This is the formula we have got, and this is electric field due to the disk, right? When the radius of disk is r, sigma is charge density coulomb per meter square, and this is point P, the distance of point P on the axis is x. Okay, so electric field due to the disk, this formula I have got. If the disk is very large in size, if the disk is very large in size, say r tends to infinity, if the disk is very large in size, say r tends to infinity, the radius of the disk becomes infinitely large. Is this formula used in all cases? Wherever disk is involved, that formula will be used, Raman. Wherever we are using disk and we are concerned with finding electric field due to a disk, this formula will be used. Anyways, so if disk is very large in size, say radius tends to infinity, which you can see in this as well. Okay, if the size of the charged body becomes very large, the distance of point P on the axis becomes insignificant, negligible, or very small as compared to the size of the sheet. So in that case, the formula which we have derived here, if I put r tends to infinity, this will give me E due to large sheet. E due to large sheet will be sigma by 2 epsilon naught 1 minus 1 upon infinity. So that will be 0. So sigma by 2 epsilon naught will be our answer. So I hope you understood. Let me highlight the answer which we are getting. Sigma by 2 epsilon naught only will be there in case of uniformly charged infinite or large sheet. Okay, sigma by 2 epsilon naught will be electric field due to uniformly charged infinite or large sheet. Sigma by 2 epsilon naught. In case of a disk, what it is? Sigma by 2 epsilon naught into 1 minus x upon under root x square plus r square. Using the same formula we have derived for infinite large sheet as well. No problem. Let's proceed further. Electric field strength due to a uniformly charged large sheet. This we have already written, right? electric field due to large sheet is equals to sigma by 2 epsilon naught at any point P in front of it. Electric field strength due to a spherical shell of uniformly distributed charges with surface charge density sigma. Okay, so in that case what we are supposed to find, let's take one sphere. Okay, spherical shell. What is this? This is spherical shell. So for this spherical shell, let's say the radius is capital R and the whole charge of this spherical shell is distributed where? At the surface. Whole charge is distributed at the surface. Now I have to find electric field at 3 different positions. What are the 3 different positions? I have to find electric field due to this uniformly charged spherical shell at a point which is present inside, at a point which is present on the surface of this, and at another point which is present outside this spherical shell. Okay, so let me denote one point here P in, another point here P surface, and another point here that is P out. Okay, so now electric field at P in, electric field at P in, electric field due to this spherical shell at inside point will be how much? How much it will be? So it will be like 0. Why? Because Q inside is equals to 0. If there is no charge inside, there will be no electric field due to this spherical shell, right? Because the whole charge is distributed at the surface of the spherical shell. What about electric field at P surface? Electric field at P surface will be K Q, because this total charge is capital Q. If this total charge is capital Q, this will be assumed concentrated at the center. Okay, K Q by R square. So you can write in this Q assumed concentrated at center. For surface point, Q assumed concentrated at center for surface point. Okay, electric field at P out, outside point, that will be K Q divided by distance square. The whole charge on the surface of this spherical shell will be assumed concentrated at center. So for P out, what will be the distance? See, let's see, this is distance x such that x is greater than capital R. So in that case what we can do? Electric field at P point is KQ by R square, right sir? Right, but it depends on what point you are considering. If you are considering inside point, then there will be no electric field. Okay, if you are considering surface point, at surface you can assume the whole charge on the surface to be concentrated at center. So for surface point you can directly write KQ by radius of the spherical shell square. Now for outside point, the whole charge will be concentrated at center, no doubt about it, but the distance will be taken according to the location of the point. So how far the distance of the point is from the center of this spherical shell? So from the center I have taken that distance as x such that x is greater than the radius of the spherical shell. So KQ by x square, this is my electric field at outside point due to this spherical shell, and the same reason Q is concentrated at center, assumed. Okay, so if this is the case, how we are supposed to make graph between electric field graph between electric field and the distance x. So here what I will tell you here I will suggest you to put x is equals to capital R, because that will tell us about the electric field at the surface point. So electric field before radius r was 0 in this case, because there was no charge inside. So in this case what we can mention, we can say that electric field magnitude at x is equals to r is given by kq divided by capital R square. So electric field magnitude will start reducing as the distance increases, like this. Okay, so you can say this was the magnitude kq by r square initially. After that, E at P out is inversely proportional to x square. So it is parabolic. Is that clear? Not parabolic, hyperbolic. No problem? Chalo. Let's proceed further. So this is the graph. Please remember, many a times in questions it is directly asked. So you have to remember it clearly. Graph between electric field and the distance of the point from the center of the spherical shell. Let's proceed further. Electric field strength due to a solid non-conducting sphere of uniformly distributed charges with surface charge density rho. Okay. So we are given a solid non-conducting sphere. So let's draw a non-conducting sphere. So this is a non-conducting sphere where positive charges are present everywhere. So positive charges are distributed everywhere, and it is not a conductor. So positive charges are not going to flow on the outer surface of the conductor, they are going to stay wherever they are. Now what we are supposed to find in this, we have to find electric field due to this non-conducting sphere or this solid sphere, due to this solid sphere at different points. Let me mention the points like this. So let's change the color to green color. Okay, so I am taking different points. This is my center, not my center, this is the center of the solid sphere. Now I am taking a point, let's say this is P inside, then we are taking a point that is P surface, then let's take a point which is P outside. This P out is actually x distance away from the center, and this x is greater than radius of the solid sphere. No problem. Now what we are supposed to find here, we have to find electric field at different points. So electric field at outside point I am writing first. Electric field at outside point will be how much? The whole charge will be assumed concentrated at center. Let's say the total charge is plus q. So the whole charge will be assumed concentrated at center. If I am assuming the whole charge to be concentrated at center for an outside point, I am writing electric field at P outside will be equals to kq divided by distance of point square, that is x square. Q is assumed concentrated at center. Now electric field at surface point EPS is equals to, that also is going to work similar, kq by r square, because same, q is assumed concentrated at center, same as we have assumed before. Now this will be the significant change as compared to spherical shell. In spherical shell there was no charge present inside, but in this case what is there? Charge is distributed all over its volume. So in that case what we are supposed to find? See, what I will do, I will try to make a sphere here inside, a sphere which is having the radius as the distance of P inside, or the distance of inside point P from the center. And what is the radius? The radius will be given by, let's say the radius is given by x. Why I am taking x every time? Because x is just a variable. X can be less than r or x can be greater than r. It depends which point we are considering. For now we are considering the inside point. So for this inside point, x is the radius of the sphere which I have considered passing through point inside point. Okay. So now what we will do, electric field at inside point P in will be is equals to K Q inside divided by distance square. What is distance square? X square. Okay, because that is the radius of the sphere which we have considered for writing electric field at inside point. No problem, but I don't know what will be the charge inside this sphere. Do we know the charge which is present all over the sphere, all over the volume? Yes, we know. What is the charge? Capital Q divided by total volume of the sphere. So capital Q divided by total volume is Q upon 4 by 3 pi r cube into the volume of this small sphere which we are considering. So Q inside is total charge divided by total volume into volume of what we are considering. What is that? 4 by 3 pi x cube. So from here we will get 4 by 3 pi cancelled, and this will give us capital Q x cube divided by r cube. Okay. So from here we can say electric field at inside point P in is equals to K by x square into what is Q in? Q inside capital Q x cube by r cube. Capital Q x cube by r cube. So from here we can say K Q x divided by r cube. Is that clear? So K Q x divided by r cube which we are getting here. So you can say either you can write electric field at inside point as K Q x divided by r cube such that x is less than r, or you can write electric field at inside point as K Q by r square dot x by r. So you can say K Q by r square as electric field at P surface into x by capital R. So in this also you can write. I am highlighting so that you are able to focus that there are two ways of writing the same electric field at inside point. What is that? Either you write K Q x by r cube, or you can mention electric field at surface point into x by r. Okay, so that you have to keep in mind. So here what we can say, how will be the graph? If we have to make a graph between electric field and the distance of point from the center of the solid sphere, what we can, how we can draw? Just focus here. See, this is electric field. So this is distance x from the center of the solid sphere. This is electric field due to the solid sphere. Okay, different points. So now at x is equals to r, I was already having an expression for electric field for x less than r. What is that? Electric field for x less than r is K Q x divided by r cube. So in this case what we can do, E is directly proportional to x, that means it is a straight line. Y is equals to mx. E is directly proportional to x, that's what is coming from here. This board has started behaving abnormally again. When it is not in mood, it starts like this. No problem. We are also in mood of studying, we will do it again. So now what will happen? This is a straight line. For inside point, this will be a straight line where electric field E will be directly proportional to x. Okay, and after x is equals to r, when it reaches a magnitude here, the magnitude here is K capital Q by r square. So after reaching the maximum magnitude at surface, it starts reducing again, just like before in case of spherical shell, and here electric field will be inversely proportional to x square. Okay, but inside also electric field will be there, and it will be directly proportional to the distance of the point from the center of the solid sphere. Is that clear or not? I hope all of you understood. Clear? That's how we are supposed to draw graph of electric field due to the solid sphere at different points, whether inside point, surface point or outside point. Let's proceed further. So electric field strength due to a solid non-conducting cylinder of uniformly distributed charges with linear charge density lambda. Okay. So what we can say, instead of taking linear charge density here, I will just prefer to write volume charge density. Okay, volume charge density rho. Okay, so first of all, let's consider a cylinder at least. Let's consider a cylinder. Okay, and this is a solid cylinder, non-conducting solid cylinder. So everywhere we can say that what will be present? Charge will be present. Everywhere charge is present. So wherever blue color is there, charge is present. So all over the non-conducting cylinder, charge is present. Let's say the charge density will be given by rho, charge per unit volume. Let's say the length of the cylinder is capital L. Okay, I am taking different points inside. This is the axis of the cylinder. Okay, I am taking a random point, say let's say I am taking a point P in here, then I am taking a surface point like this, P surface here, then I am considering another point, let's say somewhere here, P outside. Okay, so we have taken 3 different types of points. Tharun, Idu. Hi Tharun, hi. So there are 3 different type of points. What are those points? One is P inside point, one is outside point, and another is a point which is present on the curved surface area of the cylinder. Now what we are supposed to do here? Okay, let's see. If I have to find electric field at P out, I shall assume whole charge to be concentrated at the axis of the cylinder. Okay, so from here what we can write, electric field at P outside will be K Q by, or instead of writing KQ, you can say this lambda we can use as it is. Okay, I am writing here as and this lambda also I am referring here. Why? Because I know that due to a linear charge, infinite linear charge, electric field at point P is given by, suppose if this distance is r from the axis of the charged wire or the linear charge present, then I can easily say that if this is charge per unit length lambda, electric field at point P, EP is given by 2k lambda by r. So for using that, I have mentioned lambda again, and I am assuming for an outside point P, that is this, I am assuming the whole charge to be concentrated on the axis of the cylinder. So I can write 2k lambda by r, assuming whole charge to be concentrated on axis of cylinder, on axis of cylinder. Let's consider that the distance of point P from the axis of cylinder is x. So instead of small r, I am writing it as cap x, 2k lambda by x. If I have to find electric field due to this cylinder at P surface, so at surface point as well the same story will be followed. What we are doing, I am assuming the whole charge that is present in the solid cylinder to be concentrated at the middle line, that is at the axis of the cylinder. So in that case what we can do, I am assuming the whole charge to be present at the middle of the cylinder, that is at the axis of the cylinder. So in that case what we can do, 2k lambda by capital R, where this is radius of the cylinder, okay, where this is radius of the cylinder. One thing which you have to note here is, we are not considering a finite length of the cylinder when we are writing all this. Is that clear or not? When we are writing all this, we are not considering the finite length of the cylinder. This is for infinite length cylinder, such that the charge is distributed according to charge per unit length lambda. That's it. Now only one case is remaining, and that is what crucial. That's what crucial is, because upon that we will have to define how much charge is present till the time we are considering this point P inside. So if I am making a cylinder which is having a radius equal to the distance of point P inside from the axis of the cylinder, like this, then I will have to decide what is the charge present inside this. What is the charge present inside this cylinder which I have made according to the radius of the cylinder which I am making for P inside point. So if you are not able to see where is P inside, I am highlighting it. P inside is present here. Okay, this in yellow color, P inside is present. So I have highlighted P inside, and the radius of P inside is x from the center. Now what we are supposed to write? How we are supposed to write the charge concentrated here? So in this case, if rho was given charge per unit volume, and if we are considering the length of the cylinder as capital L, I am writing rho is equals to charge per unit volume. Okay, charge per unit volume. So you can say charge by area into length, charge by area into length. Do you agree? So charge per unit length is this, no problem. So here what I am doing, I am assuming the total charge present here is capital Q divided by total volume, that is pi r square, that is x square, because x will be taken as the radius of the cylinder. Okay, so here we are taking the radius of the cylinder to be full, because we have to find out what will be the charge present inside the cylinder, and that will be, we will be able to find only when total charge capital Q divided by total volume of this cylinder, that is pi capital R square into L, capital R square into L, that is charge per unit volume into volume of the cylinder which we are considering. What will be the volume of cylinder which we are considering? That will be pi into radius of that cylinder x square into length of the cylinder L. So this will give us, if I write it like this will cancel pi, this will cancel L, and what will be remaining? Only capital Q x square by R square will be remaining. Okay, that is rho, capital Q x square by R square, charge per unit volume. Okay, actually rho is already over, rho is this much only, rho is equals to charge by pi R square L. So this was rho, I have multiplied rho into pi x square L, which is giving me this q x square by r square, or you can say this is our charge inside. So I am making this in bracket. What we are supposed to use here, what is there in the charge inside, that's what we are supposed to use. Okay. So I am highlighting this. Where is it? So I am highlighting this which we have written. Q inside is this much. This is our Q inside according to whatever values are given to us. If this is our Q inside, what we will do? We will assume this whole charge. We will assume this whole charge to be concentrated at the axis of the cylinder. If we assume this whole charge to be concentrated at the axis of the cylinder, we can write charge per unit length. Okay. So we can write this as electric field is equals to K lambda 2k lambda by x, and electric field is given by 2k lambda by x. What will be lambda? Value of lambda will be charge per unit length. So what will be the charge per unit length here? Lambda is equals to q inside by length L, and it is present here, pi x square into L, q x square L by r square. So if you ask me what will be value of lambda, q inside by length L will be the value of lambda. So in this case what we can do, what is this? Electric field at P inside. So now electric field at P inside will be given by 2k lambda by x. Instead of that I am writing whatever is lambda for the charge present inside, that is lambda is equals to q inside by L. So lambda is equals to q inside by L will give me these values. So from here I am writing 2k by x into q inside by L. Q inside by L is q x square by r square. So from here we can get, what will be the value? From here we can get x cancelled, and this will be coming 2kq by r square into x. So this will be our formula. I am highlighting it for our reminder that this is the expression coming for electric field at an inside point due to a solid non-conducting cylinder. So electric field at an inside point due to a solid non-conducting cylinder will be given by this 2kqx by r square. Is that clear or not? Electric field due to a non-conducting solid cylinder at an inside point Pn will be given by 2kqx by r square, where x is the distance of point V from the axis of the cylinder, and here you can mention that x is less than r. Okay. No problem. Let's proceed further. So motion of a charged particle in electric field, and we will mention velocity, distance travelled and kinetic energy of the particle as well. So how we are supposed to write about the motion of a charged particle in electric field? You can say that in presence of electric field, force on charged particle F is equals to Q into electric field. Hence you can say acceleration is equals to force upon mass, or you can say Q into E divided by M. If this is the acceleration in the presence of electric field on the charge which is present in that region, what we can say? We can say that we have already remembered these equations. V is equals to u plus at, right? X, or you can say S is equals to ut plus half at square. So we can actually apply when we are knowing that acceleration is constant, it is not changing with time, because q into a is not going to change with time. So that's why we can mention that u is equals to 0. If u is equals to 0, v is equals to qe by m into time t. So this is what we are getting in case of velocity at any time t when the charge is released in presence of electric field. What else? We can mention about distance as well. If u is equals to 0, S is equals to half QE upon m into t square. QE upon m into t square. So in this case, what we can say? V is equals to QE by m into t. S is equals to half QE by m into t square. So we can say that distance travelled will be given by half QE by m into t square. We have just put the value of acceleration here. The acceleration which we are getting in presence of electric field is QE upon m, because we are getting electrostatic force in the presence of electric field on the charge, right? So that's it. So now we have written velocity, we have written distance travelled. What about kinetic energy? We already know the value of velocity, so I can write kinetic energy directly. What is that? Kinetic energy is equals to half of m v square. So you will get kinetic energy as equals to half m q square e square t square divided by m square. So from here you can say kinetic energy is equals to half m q square e square t square. So that is the kinetic energy coming in the presence of electric field for the charge q having mass small m. Is that clear or not? So this is the expression for kinetic energy, q square e square by 2m into t square, and the rest are expressions for velocity and distance travelled. What if the motion of charged particle we have to study in presence of electric field if the charged particle enters perpendicular to electric field? Suppose electric field is like this. Our electric field is like this in the upwards direction. So if this is the direction of electric field and charged particle is coming like this, u, so the motion of charged particle will be like this, right? Let's say this is x comma y. So the motion of charged particle will be like this. How it will be? It will be parabolic path. Parabolic path. How? Acceleration in y direction will be equals to q into e divided by m. Right? Acceleration in y direction will be equals to q into e divided by m, because a force will be applicable on the charge in the y direction due to electric field present. So you can say if this is charge q comma m having charge q and mass small m, and this is the particle here having charge q mass small m, every time there will be a force acting on this charge in the upwards direction, that is qe. Okay, so force divided by mass, I have written acceleration here, no problem. So once I have written the acceleration, I can mention that u x is, or you can say one thing, velocity in x direction is always going to be how much? Velocity in x direction is always going to be u only. Whatever the initial velocity was, the same initial velocity will be remaining for the whole journey. Why? Because in x direction there is no external force acting due to the electric field present here. Okay. So what about velocity in y direction? in velocity, in case of velocity in y direction, there was no initial velocity in y direction, but due to the presence of electric field, what happens? The path of this particle changes like this, okay, and instead of following a straight line motion or a straight line path, it follows a parabolic path. So you can say that there will be accelerated motion in y direction, so that's why its velocity will increase, okay. So its velocity is ay into t, because initial y direction velocity was 0, so I have not mentioned it. So now I can write qe upon m acceleration into time t, okay. So at any time t, v is equals to under root of vx square plus vy square, so that will give us u square plus qe by m into t whole square under root. So this will be the velocity given at any time t, okay. Other than this, what we can use? What else we can use here? We can say that in y direction, or instead of y direction, in general also we can write from the same equation, this equation which we have written, we can actually write another equation like this: v square minus u square, this is net velocity final, this is net velocity initial, is equals to what it will be? qe by m into x, but this will not be applicable here. Why? Because we are not having any electrostatic force in x direction, so that's why I am not writing any velocity change in x direction. This we have already given, so net velocity expression will be given by this. Let me highlight it for you. Net velocity expression will be v is equals to under root of u square plus qe by m into t whole square, okay. So this is what you have to think about when we are having electric field perpendicular to the direction of entry of the charged particle, okay. What else we can suggest here? Distance travelled in y direction. If you have to calculate distance travelled in y direction, so y is equals to half into qe by m into t square, x is equals to u into t. No problem, that's it. So that's how we are supposed to analyze when a charged particle is entering perpendicular to electric field, or a charged particle is entering anywhere in the region where electric field is present, okay. So all the best, take care, enjoy your day, have a nice time, keep practicing more and more problems, and ask your doubts in the next class. Don't miss the next class, please stay connected. Bye, take care.